Hello. Don't see anyone who has joined, so let's wait.
Hello.
Hi, Rohit. We'll just wait for a minute, see if Saransh is going to join, or then maybe we can make a start. I see Saransh is joining in as well. Let's give him a minute, then we can start. Hi, Saransh. Can you hear us?
Yes, Dominic, I can.
Yes. Okay. I hope you both can see my screen as well. So, assuming that, let's give it a start. So, yesterday we closed the call with an example that we started to take. So we looked into the normal distribution only yesterday, right? And we looked into the rules or the properties of the normal distribution which we have. Then we also looked into something which we represented by the letter Z, which is also known as a standard normal variable. So later on, as I've already told you, note uh, later on this variable will be used to perform a statistical inference test. Okay, let me just tab this, and this test is also called the Z test. Okay, so we're going to see a small demo of this Z test. We are not actually going to perform the Z test right now, it's too early, but we'll see one of the applications. But then before we closed yesterday's call, we also see or we also saw one example where we took the questions. So we gave a scenario. I have a standard box of cereals, which whose the company is claiming that the average weight is 2.295 kg. So it is 295 grams. The standard deviation of only 25 grams. Right. So this is what they have given. Remember here, I'm not going to explicitly convert kgs into grams. If there is a data set, we are not going to change the scale. We'll keep the scale to what we are already provided in the data. The data is captured in kgs, then we are going to consider the scale as kgs only. We're not going to consider the scale in grams because we can understand or convert kgs into gram, right? That's not what we are going to do. Okay, please don't do that. Please don't change the scale. I'll tell you why. Irrespective of whether you change or not change the scale, it's not going to matter anymore, because today we are going to look into how to check a distribution being let's say normal or not. How are you going to find whether a distribution is going to be normal or not? And then we are also going to answer these questions because it is left, right? We only calculated the Z value yesterday. We tried to calculate the Z value. We have not really finished it. I think we calculated the Z value for the first one. But then if you look at the formula of Z, let me just zoom this out a little bit. If you look at the formula for Z, it is taking any random variable X. In this case, that's the ask or the question that I'm trying to answer, right? So if this is the point on the standard normal distribution graph that I'm interested in, then X becomes this point. Mu, I already have the mean, and then I have the standard deviation. Now I already know that all of these are in scales, right? So if X or this values are given into kg, then you can clearly see from this example that the numerator is going to contain kg, denominator is going to contain kg. That kg and this kg is going to cancel themselves out because scale on the numerator is going to be cancelled out or ruled out by the scale in the denominator, which both are the same in this case, because we are using the values which are relevant to that scale only. Hence, the value that we get for z is scaleless. Okay, so this value is without scale. So it does not contain the original scale of the data. In this case, we have the data in the kg scale. The z value is not going to be of any scale. It's just a number. And we found out, I think yesterday, this number came to something like minus 0.6 or something. But we need to recalculate that. We have not really done that in a proper way. So we have to redo that. And then what we are going to do is that, because we have a very hefty kind of a formula, as I already informed you yesterday, maybe I'm going to post an announcement in our LMS with the formula. The formula is really, really very complicated. But if you understand the formula, it becomes easy. So maybe I'll show you the formula, and then maybe we can have a quick look at what that formula really means, or what that formula can be deciphered into. Right? So that I can show you. The reason why we did not look into the formula is because we already have statistical softwares. We have softwares by means of which we can calculate the values, and hence we do not need to look at the formula, right? Because we have already seen the case with the z value. So why I am so stressing on the z value will be very clear to you. So let me just show you the formula once, right? So I will be showing you the formula once. Give me 1 minute. I'm trying to paste the formula, which may not happen over here. So give me a minute. Let me see how I can present the formula, because if I write the formula, I don't have a good touch screen kind of a thing, so it may not work. So give me a moment. Let's see what other. Okay, yes, I can do it in this way. Yes, fine. Let's do one thing. Yeah, let me share this thing here. So where is this? New share. Yeah, I will share this Word document. So I hope you can see my screen now as well, where you can see the formula. Now, the one that I have written on top, this is the original formula. And I know there is some value of z, okay, basis which I have got this new formula. So this I'm going to call new. Okay, this is the derived formula or a new formula. And this one is basically the old formula. So, or the original standard formula. So what we are doing over here is we have mean. So this is standard deviation, and this is the mean, and we have the random variable, and we have the variance. Right. So if you carefully look at what is happening over here, then I can clearly convert this equation into this equation, where I can say that this value of z, okay, this value of z represents x minus mu divided by sigma. Right, this is what we said. Z is equal to x, or any random variable x, which is part or assumed to be part of that normal distribution, minus mu, which is the mean of that standard normal distribution, divided by the sigma or the standard deviation. See, if you simply take that much part out of this part, barring the square part, then you can clearly see this is z square by 2, because this becomes 1 by 2, and then the rest of the parts becomes z square. Then you might be wondering, where does this one go? The standard deviation should have been over here. It is no longer required, because now this formula or this epsilon is actually normalized. The reason why I didn't wanted to discuss this yesterday is not because this formula is really complicated. Yes, I do understand this is complicated, because this part in the formula, looking at a mathematician's view, is a constant with a variable. So almost everything in this part is actually constant. This denominator 1 by root under 2 pi is so small that adding a sigma to the multiplication is really not going to matter anymore. So that's why 1 divided by sigma multiplied by root under 2 pi is almost the same as equal to 1 divided by root under 2 pi, because it doesn't matter how much is the value of this, because this value is very, very small, multiplied by epsilon to the power something that we have already derived into this form. And I'm going to tell you why or what advantage this has. Now, this is the epsilon value. This is like the logarithm scale, as I told you yesterday. Now, The reason why we need not know all of these things is because we already have R, we already have, let's say, Python, we already have Excel, and these kind of formulas are already embedded in there. So I don't really need to know the formula only for, let's say, academic kind of a purposes. But maybe if you are, let's say, referring any papers later on at a later stage, if you're going to look at academic papers, then you will be finding formulas like this. So you should know the definitions. You should know what is happening over here. Like why I said that this part is almost always approximately equal to a constant is because this value doesn't matter, right? Now this function, from any mathematician's point of view, because there is a logarithm inversed into an epsilon, is going to take a structure which is going to be similar to what our Normal distribution is. Okay, so that is the reason why this function describes the probability density function of any normal distribution. Then what we have done, we have taken this part out of the formula, right? This x minus mu divided by sigma is basically z. So we have taken that part out of the formula and we have converted that as z. Now what is happening is, yesterday, if you remember, when we calculated z for that question number 1, it came to approximately 0.6 minus 0.6, right? Because this is a value, now I am getting an absolute value on top of epsilon. And what advantage it does is that it helps us smooth this graph. Now this is going to be difficult to understand because, or I can explain it to you in a different way, although we are going to look into calculus at a later stage. In any case, when we have a smoothened graph like this, because I already told you how, no matter how much you extend this part or that part, it's always going to be parallel to the x-axis or the horizontal axis, right? So after this point in time, there is no point of stretching the graph. Now anything that I want to analyze in this kind of a distribution is basically represented by a mathematical formula or a concept which is known as area under the curve. So anything that is under this curve, anything which is covered as an area under this curve, is going to be what I will always be interested in. Right? Example given yesterday when I looked into that diagram. So I created a normal distribution. I assumed that it is a normal kind of distribution, where the Sarang had also asked the question as to how did we assume. So that we are going to answer today. And then we took a point, right? So this is the mean, and then I took a point, right? If I remember the question correctly, now this point was 0.28 or something, and this mean was something like 0.295, if I'm not wrong. So average weight of each and every breakfast cereal box is 0.295 kg, where my interest point or my tipping point is going to be 0.28. And I am interested to look into the probability of any box falling into this region, right? So what I'm trying to do here is I'm trying to understand what is the area beneath that curve. And that's where this conversion is going to help. Why? Because when we look into the calculations now, this is where, and this is a very important thing to remember, yeah, because this is what exactly what we are going to do when we are going to do the calculations. I am drawing an arrow. Okay, always remember this arrow. This arrow is giving the progression of the data. So any value which is small is on this side, any value which is large is on this side. Okay, you will see the experience of this or the effect of this when we look into the actual calculations into Excel. When we do any probability calculations over here, the Z value almost 100%, near to 100% of the time is going to come into minus. If it is going to come into minus, we are simply going to put that Z into this formula. Okay, I put that Z into this formula and I get the function of Z. Okay, because earlier it was function of X. I have replaced this part as Z, and hence I can call this a function of Z. I simply impute the value of Z over here, and then I get some answer. I take this answer, and this becomes the probability of anything which is under this area of the curve on the smaller side of my tipping point. So that is what my question is, right? I want to know how many boxes can be there, or if I buy a box, what is the probability that the size of the item which is there inside the box is less than this value, right? Which is my random variable, basis which, and taking the mean and the standard deviation, I calculated the Z value. And then I put the Z value into this formula, and then I get the output of this formula. The output of this formula will be something. Okay, let's say the output of the formula is x, or the output of the formula is, no, I'm sorry, it is something like dot abc. So some kind of a number with a decimal. Okay, 0.abc or 0.123. So that's the probability of an item coming in this area under the curve, right? But the progression of the numbers, as you can see, it is 0.295, 0.280 is here. So anything smaller goes on this side, anything higher goes on this side. But when I read the data, I read it like this. Okay, remember this, and we are going to use that, right? So let me clear this drawing and let me go back to my share. Okay, so now what I'm going to do, I would like to solve these problems. Okay, and I'm going to use an Excel sheet to solve this problem. So instead of doing a rework, let me just take this and put it inside an Excel sheet, and then I will share that Excel sheet with you. Give me 1 minute. I'll just share this. Please note that we already had to do a section on Excel. I believe we are going to cover a lot of things in here itself, but later on, maybe we can do a quick kind of a session into Excel where I would like to show a few things which are there, which are quite handy when it comes to Excel. So let me just share my Excel sheet now. I have copied the question into an Excel sheet. Okay, and here is the question. So I have 3 questions. I have a scenario, and then I have 3 questions. So what is the answer to the first question? Okay, what is the probability that the standard box weighs less than 0.280? So at the first place, I need to know whether this is a normal distribution or not. And then only, okay, I can apply the formula which is the z value, right? Because the z value applies to a standard normal distribution. Now in this case, I have assumed that it is a normal distribution because let's say I have all the values which are there in all the boxes that I've actually collected. So what I mean by that is I'm doing a sample mean, or I am taking the sample mean of all the samples. Okay, so let's say I have 20 samples, or maybe I can insert a row here, and then I'm going to say serial number. So serial number is basically the number of the item number. I've actually given it a number. Let's say I have uh, 15 samples. So basically I have 15 boxes. I have 15 boxes of the cereals that I've taken. And what I'm doing over here is I am taking the mean weight. Okay, so there is some mean weight here, some mean weight here, some mean weight for this, some for this, and so on and so forth, and so on and so forth, right? After I take this, if I plot this, right, so this is the first rule. If I plot this, you have to assume in this case that I have already plotted this, okay? Or sometimes the question will explicitly tell you that it is a normal distribution, right? In this case, I have already assumed that I have done such kind of an activity, and then I have done a few tests. Okay, let me tell you what those tests are, and I'm also going to share you that list with you. There are certain tests. I know of a certain list of tests which we can do to do this testing. And overall, I know of at least 7 kind of tests that we can do. So I'm going to look into the basic tests first, and then the advanced ones are what I'm going to look into at a later stage, because we won't understand those right now. The first test I do, I have calculated the mean of the sample. So AA is the mean or average weight of the sample one. BB is the sample mean or the average. I'll just write this as the average. Yeah. So this is like the sample, sample ID, right? So I have given it a sample ID. Sample ID 1 has a mean weight of AA, then BB, then CC, then DD, and so on and so forth, right? Now, if I have this, then I try to plot its distribution. Okay, so how do I plot the distribution? I do the histogram, right? Clearly, we saw that if I want to create the PDF, I simply take X and Y, and then I create the histograms, right? I simply create the histograms. So I take the histograms using the bins, right? So let's say these are the histograms. Okay, so these are the bins, and I have a structure which is something similar to this. Right now, I try to understand what is the distribution. If I join the dots, then it becomes a PDF. This looks like a normal distribution. Why? Because this represents a bell curve. If this represents a bell curve, this is not a very good drawing actually. The bell curve is going to represent something like this. If there is a tail end which is like parallel to x-axis, and then there is a peak end which is almost at the middle of the line. So let's say this is the line, and I have taken, or this is the horizontal axis, and then almost at the middle, looking by my eye only, I can see that this peak is almost at the center. Then I can assume that this might be a normal distribution. I may be right, I may be wrong, I don't know that, but this is purely based on the assumption. So rule number 1, how to identify if a distribution is normal or not? Create the histogram, create the PDF. Or you look at the histogram. Simply try to look at the histogram and try to see if there is anything that really tells you that this is going to be kind of closer to a normal distribution. Right? So this is one way. Okay. There are 6 more ways. I said there are how many ways? Total there are at least 7 ways. Okay, there can be more. At least there are 7 ways that I am aware of. I'm going to skip some of the ways because they are not going to make any sense to you right now. Okay, but I'm going to take things which we have already learned. Again, I'm going to draw this. Again, I will draw this. I thought somebody was saying something. Is there any question? Okay, I think there are none. So yeah, so let me just, okay, there is a chat. Are these all different sample means or mean of a single sample? No, this actually Sarang, this one is the mean of this sample. So what I mean by that is, I'll just be clear with you. Yeah. So this sample ID 1 represents a sample from a population. Let's say I have a population of, I don't know, 100,000 boxes, and I have taken a random sample out of this. I have randomly selected 50 samples. Right? I selected randomly 50 samples. I have marked that experiment as sample ID 1 or experiment ID 1. The average comes out to be AA. Then I put this 50 samples back into the population. Again, I shuffled the population, took another 50 samples. Okay, did you get my point? I took out 50 boxes from a big box or a big factory floor. I named that or marked that as a sample ID 1. I took the mean. Then I put that back. Again, I'm going to take 50 random samples. Some of the samples are going to coincide, but maybe many other samples are not going to. Then I mark this as 2 and I take its mean. So it comes, let's say, BB. Again, I put this 50 back. Again, I take another 50. I mark this as 3. I take the mean. Again, I put, right? This is how I'm doing it.
Okay, so all these samples should follow a bell curve, right? So these 15 samples,
No.
if you draw
No, each and every sample will not follow a bell curve. After you have taken all the samples, then you draw the histogram. Then it will follow a bell curve.
okay. Okay, so after all, so this bell curve will represent all the samples and its mean.
Exactly, right. So let's say this is one bin of some samples. This is one bin of some samples. This is one more bin. This is one more bin, and so on. When I look at the diagram itself, I can clearly tell you that if this is my kind of, let's say, histogram, then it is quite clear that this looks like a normal distribution. So that is my first rule. Right, my first rule, I will look at the histogram or the curvature, and I'm going to say, okay, this curvature is really good. It represents a bell curve. It conforms to the properties that I have looked into. Hence, I can say that this is a normal distribution. Right? So only by looking at it, I am trying to do an assumption.
Okay, and then mu is the sample mean.
Yes. Mu is the mean of all of these samples. Mu is the mean
all of these samples. Okay.
Right. So I have taken, let's say, 15 samples. I take a sum and divide by 50. Right. So that is the sample of all the experiments that I've done. Right. Okay. Okay.
Okay.
So let me just go back once more. Let me clear the drawing. And yes. So what I'm going to do now, that was the first technique, right? So the first technique is I simply make an assumption. Now the second technique. This is going to be interesting. The second technique is I look into the distribution, which is something like this. Okay, I've already assumed it is a normal distribution, but I need to find out something, some property, which is known as the skewness. We have already discussed what is skewness. Skewness is what? If this top section, this curve, this elevation that we have over here, falls in the middle part, then we say this is center skewed or a normally skewed kind of a distribution. Had it been the case this was something like this, I would have called it a right skewed. Had it been the case this was something like this, I would have called it a left skewed. This is right skewed because it has a tail on the right side. And this is left skewed because it has a tail on the left side, right? Now, if I look at this diagram, the skewness looks to be quite closer to 0. Okay, if I am able to calculate skewness, if there is a formula, and there is, by the way, so there is a formula of skewness. I will share that with you later on, but as of now, I'm going to use an Excel kind of formula. So if I calculate skewness, and that skewness, let's say S, the value of S, is quite closer to 0. Let's say it is approximately equal to 0. Or in the industry, what we follow is it is within a range of -2 to +2. So if this skewness value, once calculated using the formula of skewness, is going to fall within a range of -2 to +2, or it is going to be very close to 0, then I can say that this is a normally skewed data. It is not a right skewed thing. It is not a left skewed thing. And I know what happens with a normally skewed data. Mean is equal to median is equal to mode. The normally skewed data has a shape of a bell curve. I can be quite confident. I cannot be 100% confident. I can be quite confident that this is really a normal distribution. I can safely assume that safely. I cannot 100% do a guarantee. This is a probabilistic game. I will never be able to do any guarantee. There are statistical tests, by the way. Out of the 7 methods which I told you, there are at least 3 to 4 where there are certain tests that we do. Right? At least 4 are there, which are the tests that we do. The rest 3 are quite easy to understand. So that's what we are looking over here. The rest 3 are not basis any test. They are basis the formulas or the visualization. So the first thing was I looked into the histogram. It looked like a normal distribution. So I'm quite happy. This structure looks like a normal distribution. Then I took or calculated the skewness value. Don't worry, I'm going to share the formula as well. And I calculated that, let's say in R or in Python or in Excel, and I found out either the value is very close to 0 or it is within the range of -2 to +2. I close my eyes and I safely assume I think this is really a normally distributed graph, and this random variable is really normally distributed. I can start using that Z formula and that f of z and so on and so forth to solve my problem. Right? So that is the second way. What is the third way? Third way is something I would have to explain a bit first, and then only I can tell you what that third way is. Okay, the third way is how or what is the measure. I'm sorry, I should have cleared the drawing. So how much? Okay, let's say this is. Oh no, sorry, this is a very bad color. Let me change the color and let me draw the x and y axis first. So this is y, this is x, and now I'm going to take a curvature. Let me take another color, and let's say this is the normal distribution. This is kind of a bell curve. I have already checked the skewness. I've already checked the structure. Basis the structure or the nature of the curve and the skewness value, I think I'm quite sure this is a normal distribution. But then there is one more statistical measure that I take. This measure is also known as the tailedness of the probability distribution. The tailedness. What is the meaning of tailedness? Tailedness means how good is the shape with respect to the tails. So for example, how is this distribution looking with opposed to the tails? Okay, what I mean by that is, let's say if I draw another diagram where I have this as my y-axis, this as my x-axis, and then I would like to draw a bell curve. Okay, is this not a bell curve? This is a bell curve, right? You have to agree this is a bell curve. What about this? Is this not a bell curve? This is also a bell curve. Okay, what about this? Is this not a bell curve? This is also a bell curve. Then if these three are bell curves, then how do I use this new concept of tailedness? Tailedness is where if you look at this guy, its height might be less than compared to the rest too, but its tails, look at its tails, it's really spread. It's like an octopus spreading its legs and its arms, right? The spread is really big, right? Then I compare that with this guy. This guy has a little bit of a better tail. But then if I look at this guy has an extreme tail. I mean, why? Because it has very, very small tail. So this kind of an extreme case should not be there. Okay, if I look at the diagram itself, I should be able to say such kind of extreme cases I don't really agree with. I'm not going to accept these kind of, let's say, extreme things. I'm going to accept something which is really looking good for me and it is looking quite structured like this one. Okay, if you look at this one, the tails are equally sized. If you remember, I told you yesterday, if I draw a line here and if I draw a line over here, I take a distance here and I take a distance here. These two distances, D1 and D2, will be equal. This is a very important thing when we look into central limit theorem. This is going to come into handy, right? By the way, central limit theorem is also another way to calculate whether or a distribution is really a normal distribution or not. But we are going to look into central limit theorem at a later stage, right? This tailedness thing that we looked into over here, we looked into the tail over here, or looked into the tails here, we looked into the tails here. This also has a mathematical formula. It can be represented using a math. And this property is known as kurtosis. How much is the tailedness of the graph? Again, the rule of thumb that we use is that if this kurtosis value is very close to 0 or falls within a range of -2 to +2, then I say the distribution is a normal distribution. Okay, so I have three rules. One is the visualization rule. Second is the skewness rule. Third is the kurtosis rule. These are very basic steps, very basic tests. I don't need to be an expert in, let's say, statistics field to do these tests. I can do them and I can come to know whether this distribution, or for that matter, the distribution of any random variable, is a standard normal distribution or not. Right? So let's see how we can try to get this done into Excel. Okay, because we don't have much time left. So we are going to take an example. Maybe we are going to solve this problem at a later stage. If we have time, we are going to solve it, else we won't. Okay, so let's say I have some data, -3, -2, -1, 0, 1, 2, 3. Right? I want to know what is the skewness, what is the kurtosis of this data. Okay, I may want to look into the histogram as well. Let's see if I can create any graphs over here in the recommended charts. Do I get anything? I don't get anything which is really representing this. Let me see if there is any histogram. No, there is no such histogram which I'm able to see. I don't know why this is very difficult in Excel, or maybe I'm doing it in the wrong way. Right? Let me see what's that is a car. Yes, yes, you can say that, Rohit. Yes, you can say that. Also, we have not looked into projections, so we will be doing that. So yes, Fisher projection is a certain case where the kurtosis will be equal to 0. Yes, it is quite close to 0. It is approximated as equal to 0. Right, now let's say this is the value. So if I have these values, let's say I want to calculate the skewness and then I want to calculate the kurtosis. Okay, to do both of these things, I have functions. So you see, I simply typed equal to SKE and it gave me a function which says returns the skewness of a distribution. So I take this and it is asking for a lot of numbers. So I simply take this range and I say enter. The skewness is equal to 0. This is a perfectly normally distributed data set. Okay, why? Because skewness is equal to 0. Let's see what is kurtosis. If I say cut, then it gives me the formula. Again, I take the range of all the numbers. I press enter. This is minus 1.2. This is not equal to 0. Kurtosis is not equal to 0 always. Okay, like Rohi has already pointed out, there is a certain set of case when only kurtosis is going to be equal to 0. Otherwise, it won't be, right? So kurtosis will not always be equal to 0. But we have a rule. We have already clearly defined, my friend, if kurtosis is within the range of -2 to +2, if the skewness is in the range of -2 to +2, then we can safely assume that the distribution is going to be a normal distribution. Okay, so these are the range of numbers. Okay, these are the range of numbers. These are like these values, A, B, B, C, D, and so on. Right? These are the values which are like this. Right? So, and then what is going to be the mean of this? If I take mode, no, median of, what is going to be the median of these numbers is going to be 8, right? So this is going to be, let's say 0, 1, 2, 3, 4, 5, 6, 7. Okay, and then this will be -1, -2, -2, -3, -4, -5, -6. See, had it been the case, this is my range, then this will also have a skewness and a kurtosis, which is really very good. You can confirm that. I'm just making up the number so that I can prove my point. Now, if you look at this, now this has gone beyond the case. Do you really think so? No, because there is an E. It is really close to 0. If you minus this, if you see any signs like E, you just simply do one thing. You minus this value from 1, and you will see that the answer comes as equal to 1. That's because this value is so small or so close to 0 that it has to be represented by this E value. Right? E minus 17 is like 0.17 zeros, and then you have something. Right? And then if I calculate the kurtosis, let me calculate the kurtosis. The kurtosis is going to come, let's say, if I'm going to take the value, it is again -1.2. Right? Why is this kurtosis same for this range of numbers and this range of number? Because if you see, the tailing in both the cases is actually similar. The middle value is at exactly at 0, and then the tailing follows a pattern. The pattern is it is increasing or decreasing by 1 on both the sides, right? So this is the middle value, and then on both the sides it is actually increasing or decreasing by 1. So that is why the kurtosis is same in both the cases. Only by looking into these two measures, I can clearly tell you whether a set of numbers is going to be normally distributed or not. Right? So this is kind of a test that I can do. Also, the visualization test is there. Now there are 4 more tests. I will quickly tell you what their names are. I don't want you to get scared. I will be sharing that a small kind of a notepad with you where I have actually written all these names. You can try to Google them. Don't try to get overwhelmed with them because we have to cover them. Right? One method is to use an empirical rule. This is also known as a test. Okay, so empirical rule is basically a test, also known as the central limit theorem. And the empirical rule is something which we are going to look into tomorrow, because this is really a very important thing, which is just after this thing that we are doing over here. Then there is a test which is known as chi-squared goodness of fit test. Okay, that also tells us whether a distribution is going to be normally distributed or not, because it gives us a value which is also known as p-value. Then you have a test which is Kolmogorov-Smirnov test. Okay, otherwise known as Smirnov test. The Smirnov test, or otherwise known as KS test, is also an advanced statistical test. It also tells you what is the probability of a distribution being a normal distribution. And the last one is a Shapiro-Wilk test. So Shapiro-Wilk test is also another kind of test, also known as SW test. You can apply that to look into it. So now this chi-squared, KS, SW, empirical rule. Empirical rule is something which is fundamental. We will look into it tomorrow. But like the test like chi-squared and KS and SW, we are going to look at it at a much later stage. Okay, we're not going to look at it right now. Because we have some time left, let's try to solve at least one problem. Okay, let's try to solve at least one problem. So let me get rid of this. Let me also get rid of this. And let's try to solve problem number 1. Okay, so answer to 1. I want to calculate the z value. Okay, in this case, what is going to be the z value? Is equal to, I have a numerator and a denominator. So I have a numerator and a denominator. The numerator is 0.28, which is my random variable in this case. And then I have the mean, which is 0.295. Then I divide this number with the standard deviation, which is 0.025. I get the z value. This is equal to 0.6 minus 0.6. Remember the number being positive or negative. If this is negative number, then I have a distribution which looks something like this. The value falls over here. That's why it is negative. I am looking into the small side. I'm trying to look into the small side. I told you the projection is like this. So the growth of the numbers will be on this side. If I am looking on this side, then it is tending towards a negative number. So this number is indicative that I'm looking at an area under the curve, which is on the left side or on the smaller side. Right? Now I just have to put this into a formula and my job will be done. Okay, let me put this into formula and then we can close the call. Probability. Okay, I'm going to use a formula which is known as norm.dist, normal distribution. It asks for 4 values. I put the x value, which is 0.28. I put the mean, which is 0.295. I put the standard deviation 0.025, and the last value is 1. I will tell you